So friends, welcome back. I take the applications of the kinetic theory of gases further after explaining to you the case of gases, wherein we talked about the interpretation of the kinetic interpretation of temperature, the kinetic interpretation of pressure, and the Dalton's law in the case of mixtures, etc., etc. Okay, so today I take it further and talk to you about a beautiful law. Okay, B-E-A-U-T-I-F-U-L, a beautiful law. The only spelling that when I was a kid I was trying to remember it and uttering B-E-A-U-T-I-F-U-L, beautiful, B-E-A-U-T-I-F-U-L. And then my father told me that this is the last spelling that you are trying to remember and never do it again. And since then I have never done it. Of course, I have checked spellings time and again. So, the law of equipartition of energy, that is, the total energy of a molecule has to be equiparted, equally distributed. Okay. Now we see that the kinetic energy of a single molecule, this is the translational kinetic energy of a single molecule, which I can write as half mvx square is half mvy square, half mvz square, and we know that there are three axes, they are mutually perpendicular, they are orthogonal to each other, make an angle of 90 degrees with each other, and because cosine of 90 degrees is equal to 0, therefore there is no resolved part of whatever is there on this side and this side, whatever is here on this side and this side, and whatever is here on this side or this side. Okay. So we know that these directions in 3 dimensions are mutually independent, mutually exclusive, and therefore if we assign them the directions, then these are independent of each other, half mvx square, half mvy square plus half mvz square, and this is the translational part of kinetic energy associated with the molecule. For a gas in thermal equilibrium at a given temperature T, the average value of ET will be the sum of these values, half mvx square, half plus half mvy square plus half mvz square, and this is equal to 3 by 2 kVt. So now there are no preferred directions. All directions are equally preferred. That means it is a matter of secular distribution and secular preferences where all are equally preferred. Then we can write that if we partition this 3 by 2 kVt into 3 parts, then for each part I'll get half kVt, and these are the average values in the x, y and z direction, which all appear to be equal to half kVt. In translation, if the translation is in one dimension, of course the motion is straight line along, say, x-axis or y-axis or z-axis, so this value half mvx square, half mvy square, half mvz square, it comes to a single direction and it is half mvx square. This is called 1 degree of freedom. Okay, freedom of the molecules to be moved all by themselves in a defined direction. Well, if the translation is in a plane which is 2D, 2-dimensional, again a straight line, on say xy plane or yz plane or zx plane, okay, So that way, taking xy plane, we have these two values, and then we define that there are 2 degrees of freedom. Okay. If the translation is 3 dimensions, that is, it can move anywhere, okay, in space, then we can describe the x direction, the y direction, and the z direction, okay. And in these directions, we have the average values this, and therefore we say that there are 3 degrees of freedom. This is all about monoatomic molecules. Oh, molecules. Okay. This is about monoatomic molecules like argon, krypton, xenon, okay, helium, etc. The noble gases. Then, if we have a diatomic system like O2, N2, etc., nitrogen, oxygen, etc., then there are 2 atoms like this associated with the system. Okay. The system of these 2 atoms, which comprises a molecule, they have a center of mass. For oxygen and for nitrogen, the 2 gases, are other cases of diatomic molecules, because both the atoms are akin to each other, similar to each other, therefore their center of mass must lie on the line joining these 2. Now, let's inquire. If they have a freedom of rotation, then the answer is yes. If I define an axis which is perpendicular to the line joining the 2 of them, going through the center of mass of the system, okay, then if there is one axis and one axis, this is the system, and where is that? Okay, thank you. So let me tell you, if my 2 atoms are on the edges of this rod, okay, the line join, the center of mass, then I can have, suppose if there is an axis, okay, which, let us say if this is the x-axis, then there is an axis perpendicular to it, and about this axis, this rotates like this. This may rotate like this. Then there is a perpendicular axis which is perpendicular to both of them, and which is the z-axis, then the rotation can be like this. So there is a freedom to the diatomic molecule to move in about 2 axes. Axis 1, which I have shown here, axis 2, which is basically an axis which is passing through the center of mass and perpendicular to the plane of the board. Okay. Then we have the rotational kinetic energies associated with them. We can write them as half I omega 1 square, half I2 omega 2 square. Okay. And remember that omega 1, omega t are the associated angular velocities, and I1 and I2 are the moments of inertia about the axes 1 and 2 respectively. Okay. So now, according to the equipartition of energy, we have 2 more these things, and this also turns out to be equal to something like these are, all these parts are equal to each other. So there are 5 degrees of freedom associated with that. 3 of them are translational and 2 of them are rotational. We consider right now that the rotator that we have here is a rigid rotator. What does that mean? Rigid rotator, it means that no vibrations are allowed, because the atoms may vibrate also. Okay. So far, in the law of equipartition of energy for a diatomic and monoatomic systems, we have seen that there are degrees of freedom which are the 3 degrees of freedom in the 3-dimensional space for translation, and 2 degrees of freedom in that space which are rotational degrees of freedom. So I talked to you about the rigid body oscillations which are associated with the oxygen molecule, for example, and there I said that no vibrations will take place in such a system in rigid body oscillators. Vibrations, however, do exist. Even in the oxygen molecule at high temperatures, or for example in the case of carbon monoxide, CO, of course in the case of CO, the center of mass will not be in the center, because the carbon and oxygen atoms having the atomic masses 12 and 16 respectively, there it will be somewhere nearer to the oxygen and farther from the carbon. So vibrations exist, and vibrations, as I told you in the case of springs, that the force is directly proportional to the displacement, and it is equal to some constant k times the coordinate of vibration, that is y. Of course, the k is the force constant in the system and y is the vibrational coordinate. So there is a contribution of vibrations, and this why I write as energy of the vibration EV is equal to half m dy over dt whole square, which is the velocity component, plus half ky square, which is the component due to the displacement. Look here, there are 2 terms for vibration, and therefore adding up I can say that the total energy has the 3 components: translation, rotation and vibration. Okay, 3 translational components, 2 rotational components and a component of vibration. They are not, each of them are not equal, because this has got 2 contents. There are 2 contenders. So that means overall now I have 3 plus 2 plus 2. Okay, and we can say that there are twin terms. Okay, now let's note that each translational and rotational term has 1 square term, but the vibrational term has 2. One consists of y square and the other dy over dt whole square. So now there are so many children in the family, and the molecules absorb energy through each of these square terms. Okay, so there has to be an equal distribution among all these modes. Each mode has an energy equal to half kBT. Okay, so that means this distribution is equal distribution. In the case of wealth of nations, we don't have equal distributions. Okay, I visited the People's Republic of China in early 1980s, mid 1980s, and there I met with the Chinese people living their lives. And when I asked about their normal wages, who is the most paid person, then they said almost all the people are equally paid. At the time of their induction into the workforce system. But those, for example, a doctor, an engineer, and anybody who is technically highly up, the salary is 120 yuans for each person. But if there is a hard worker means hard work is given to a person, then the salary is enhanced. Interestingly, the highest paid person used to be a teacher, and that too for the primary and secondary schools. And they were given a house comprising 2 rooms, whereas the normal worker will be given 1 room set. When I asked them why, and he will be given a matching salary for interacting with the people, with the parents and grandparents of the children of their school. Of course, every child in those days used to have normally 6 parents: maternal grandfather and mother, paternal grandfather and mother, and the father and the mother. So 6 people raising 1 child. There was no concept of a mama, a khala, a chacha, and a pupi. They didn't know in the days of Mao Zedong. So even there, in that society, there was not equal distribution of wealth. There was rather equitable distribution of wealth. But in the case of nature, in the case of what is the science of statistical mechanics, which is evolved out of this very concept, it was given by Maxwell to start with, and now this is the vast science which is taught over a semester to students of master's degree in and higher degrees in physics. Well, so there is an equal distribution. There is an equipartition, meaning thereby that a Buffett or a Fowler will have the same part of the total gross national income. Okay, there has not to be a Azim Premji, and there has not to be a Guru or Katwaru like us. Okay, so this is equipartition of energy, and equipartition of energy, each degree of freedom has an equal value, and that is equal to half kBT. Very well related with the temperature, the absolute scale of temperature at which they work, and of course the universal constant, which is Boltzmann constant. This is the LEE, okay, means law of equipartition of energy. It's not for Bruce Lee. Okay, so next we talk about the explanation of the kinetic theory for the molar specific heats and their relationships among Cp and Cv. So let us apply the law of equipartition of energy, which we have only stated for different stakeholders. Okay, the translational, the rotational, and the vibrational modes of contributions. So let us take, for example, a monoatomic gas, like one of the noble gases, which have 3 degrees of translation, and the average kinetic energy therefore becomes equal to 3 into half kBT. Okay, so we can write the total internal energy of the system as 3 into half kBT into Na, the Avogadro's number. And because kB into Na is equal to R, the universal gas constant. This turns out to be 3 by 2 RT. So from here we define Cv is equal to du upon dt as constant volume. This turns out to be equal to 3 by 2 R. Okay. Now in a gas we had another derivation, and we found that Cp minus Cv, the difference of the two molar specific heats, constant pressure and constant volume, is always equal to the gas constant, universal gas constant R. So I can write from there the Cp value is equal to Cv plus R, 5 by 2 R, and therefore if I divide this value of Cp by the value of Cv, Cp upon Cv, and that gives us the gamma, and that turns out to be equal to 5 by 3, 1.67. Okay, so this is the monoatomic system where we have compared the specific heat capacities at constant pressure and constant volume. In the diatomic molecule, where we take a rigid rotator kind of a thing, okay, the total degrees of freedom is equal to 3 plus 2, 3 translational, 2 rotational, so 5 degrees of freedom. So that will give us the value of the total internal energy of the system as 5 by 2 RT. So Cv becomes equal to 5 by 2 R, and Cp becomes equal to 7 by 2 R, and when we divide the value of gamma, it turns out to be equal to 7 by 5, 1.4. Now let us take the case of polyatomic gases. And polyatomic gases have 3 degrees of translational freedom plus 3 degrees of rotational freedom, because suppose in the case of carbon dioxide, 1 carbon atom and 2 oxygen atoms. Okay, the center of mass of the system will lie somewhere in between, and there can be now 3 independent axes, like say x, y and z, passing through the center of mass, about which the rotation can take place. Okay, so they have to be 3. Plus, suppose I say maybe f number of vibrational modes. Okay, we don't know what is f right now. Let us develop it. So my internal energy of the system becomes equal to 3 by 2 kBt for translation, 3 by 2 kBt for rotation, and F into kBt, because half, there are two things, one was y square and the other was dy dt square, so there were 2 terms, so for 2 terms each of them half kBt, so it turns out to be equal to F into kBt. Okay, so if I now sum it up, so 3 by 2 plus 3 by 2 becomes equal to 3 plus F into R. Okay, Cv upon differentiation with capital T, and so Cp becomes equal to 4 plus Fr. So gamma becomes equal to Cp upon Cv is equal to 4 plus F divided by 3 plus F, which in case I take F is equal to 1, for example, in a polyatomic system, which is not true. You can take the values 1, 2, 3 like that and make the calculations. So if I take this F equal to 1, then 4 plus 1 divided by 3 plus 1 is equal to 5 by 4, and if it is 2, then 4 plus 2 plus divided by 3 plus 2, that will turn out to be equal to 1.2, etc., etc. Okay, so it all depends upon the degrees of freedom that we have, the translational, the rotational and the vibrational modes of various modes of vibration that we get. One thing which turns out, for example, is as follows, that the value of gamma falls as we go from monoatomic to diatomic to polyatomic system. Okay, now here on this side will appear a couple of tables which tell you the actual values and the predicted values, etc., for the CP or CV and other things. They are worth pondering. Pondering means गौर से देखिए. Okay, look at it, ponder. What is this thing? How it happens? And why, like that. And there, I thought first of all to deal with the specific heat capacity associated with solids and water and many things, but I have deferred that to the next lecture, okay, because it's already quite long. So in the next lecture I discuss these things plus take a few interesting problems. Thank you very much for being with me. Do question. Why I say do question? You question and we answer. Because there is a saying by a wise man. The Shahid Azam, Hazrat Imam Hussain, the grandson of the Prophet, who said that Husnul Sawal Nisful Ilm. That a good question is, Nis means half ilm. So it is the question that gives you an access to the ilm. And ilm is more than what we call ulum, that is the sources of knowledge, which is the ensemble of ilms. But ilm is more than the ensemble. And therefore, Husnul Sawal, Nisful Ilm, I want you to question, and let us, if you question. Only yesterday I had a question from one of my very old students, more than 67 years of age, who asked me something about through WhatsApp, and I was too pleased to probe it myself, to ponder and then answer, and I think that answer was correct. Okay, then see you.